So now we've talked about the different components of stress. We've taken our slices. We started off with our potato. We took our slices. We eventually arrived at our cube. We've been able to look at equilibrium of that cube to determine that even though we started out with 18 values for stress for a cube of material, we can get that down to 6 independent quantities. And I wanted to end here with just thinking about these components in a slightly different form. So at the end of the day, we want to do some math. And so what's very handy if you're going to do math is going to be to have some representation of that stress, and it ends up being a pretty easy matrix to have here. Representation, I'll spell that right, hopefully. Okay, so we're going to start off, we're going to go back a little bit, and we'll have our coordinate system here. We have our stress cube, and when we cut our potato and we did our, and we looked at those traction vectors and the components of those traction vectors, we started out, we had 3 vectors here. So we had tau z, which is in green. We had tau y, t for traction, ty on the top face, and we had tx, which is on the x face. Okay, and so then we said, okay, we can take that and we can turn that into our components that are based on our cutting planes, which in our case were aligned with our coordinate system. And that gave us some components. And we said we had normal components, and we had some shear components. Do that on the top there as well. And we can do that on this side. Okay, so that got us to the 9 stresses. So this was 3 traction vectors. Sorry. We have 9 stresses. And we've already figured out that only 6 of them are independent. And what we can end up doing is taking those and abstracting them a little bit further, and we can talk about our stress matrix. So that's going to end up having 2 squigglies because it's a matrix, and that's going to end up looking like this. So we have sigma xx, tau xy, tau xz. We're going to have tau yx, sigma yy, tau yz, and we're going to have tau zx, tau zy, and sigma zz. So that's pretty cool. It ends up being a matrix. This is actually a tensor, and I'm going to post another video so you can learn more about tensors if you want to. But what it ends up being is just our traction vectors. So that's going to be traction vector in x, traction vector in y, and traction vector in z. And if you do that, you can see I've already gone ahead and taken advantage of symmetry here so that we don't have to do any transposing of those vectors. So it's a symmetric matrix. And just to think about that a little bit more here, you can take our three vectors. So let's start with tau t, the traction vector in z. That's just going to end up being tau zx, tau zy, sigma zz. We can do the same thing for the traction vector in y. That's going to end up being tau yx, sigma y, y, tau, y, z. And in x, you can see here, we have sigma xx, excuse me, tau xy, and tau xz. And remember that tau xz and tau zx are equal. So we really only need to have 1/2 of this matrix in order to define the stress state. Okay? And whether you're looking at the traction vectors, you're looking at the stress cube, or you're looking at this matrix, the key is that all these representations of the state of stress at a point, it's an at symbol, sorry, at a point in a body. In this case, it was our trusty potato. So it doesn't matter which way you think about the stress. They're all the same. It's all equivalent. And the picture, like we have it here, and the matrix are just telling you the same thing. In our case, I think the thing I want you to think about a little bit is that in our case, we used slices in the x, y, and z planes. So that was our choice. We could have chosen any set of orthogonal planes. So how would this have changed if we had done that? In the end, we would still end up with all these different components. But for the potato, with a certain number of forces that are acting on it, we could have gotten different values. So the process would be the same. We'd still arrive where we did in terms of our variables. We wouldn't have maybe x's. We'd have some other letter to denote these other orthogonal planes. But the values wouldn't be necessarily the same because the stresses are oriented in different directions. And so that's something that we're going to talk about next, talking about the stress transformation.